Hello, folks. Welcome back to MJ School of Mining and Geology YouTube channel. In today's session, we are going to be dealing with three theories of rock fracturing. These theories include the Mohr's, the Stacey's, and the Griffith. Okay. So I wonder if you ever wondered why rocks they break the way they do. So stay tuned. In this video, we're going to be understanding the forces behind the rock failure. Okay, stay tuned as we break down these concepts with clear explanations and the real world applications in geology and mining. But I'm sure you know what I'm gonna say. Please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. Stay tuned. So, um, basically, in geology, the fracture is just the break or discontinuity in a rock where there has been little to no displacement parallel to the fracture surfaces. The fractures occur due to stresses and can influence rock strength, fluid movement, and the mineralization. Okay. So, the causes of fracturing, it includes tectonic forces, that is to say, compressional forces, where things get to be squeezed, or the rocks get to be squeezed, forming reverse faults or thrust faults, and then also the tension forces, wherein the rocks are getting to be pulled apart. Okay, the rocks are getting to be pulled apart, creating some joints and normal faults, and also the shear stresses causing the rocks to slide past each other, leading to what you call strike slip faults. Okay. And then we also have got the thermal expansion and contraction. That is basically what we see in the mud cracks. Okay. That's basically what you see in mud cracks. But we know that the rocks will expand when heated and contract when cooled. This in itself, when this expansion and contraction, they will create what you call the internal stress. So now we know that in arid environments, mud cracks form when wet sediments they become to be, or they dry and shrink. Now, this would create the polygonal fractures, and these polygonal fractures are known as what you call, or are known as the mud cracks. Okay. So basically that is that. And also the another cause of fracturing could be the exhumation and erosion, wherein deep-seated rocks are under high pressure. Then when erosion removes overlying materials, the pressure would decrease. Now this pressure release leads to expansion joints seen in large rock domes, like in granite batholiths. Okay. And then also the fluid pressure. We know that the high fluid pressure will always weaken the rock bonds. Okay. Will always weaken the rock bonds, now forming the fractures. And also the chemical weathering. We know chemical weathering, the acidic water will dissolve things like calcium carbonate. Then now they will form the sinkholes and the caves. Sorry. So basically, that's how the fractures they get to form in geology. Okay. Now, this rock fracturing is a fundamental process in structural geology that occurs when stress exceeds a rock strength. We know that when the strength of the rock it has been exceeded, now that rock will start to fail and it will fracture now. Okay, which is why this understanding these theories would help the geologists and the engineers to predict the rock behavior in natural and artificial settings, such as the mining and petroleum extraction, and also in tunnels and other things. So there are several theories that explain how and why rocks fracture under different conditions. These theories consider factors like stress distribution, material properties, and fracture mechanics. Okay, and like I said, the theories include the Griffith theory, Mohr theory, and Stacey's extension strain criterion fracture of a brittle rock. Stay tuned as we're gonna be breaking down this concept into greater detail. Okay. Um, The Griffith theory state that the um, tensile stress induced at or near the tip of an inherent crack exceeds the molecular cohesion strength of the materials. So due to the difficulties experienced when evaluating the surface energy of the material, this criterion was later modified by several authors. The modified approach considers the stress concentration at the tip. Okay. So don't worry, I will break it down for you so that it makes sense. Now looking at the Griffith theory, we are going to be considering the we're going to be considering the where is this? We're going to be considering what you call principal stress. Okay, so the principal stress, it will be this, okay, which is the maximum principal stress acting vertically. So this one, it will be the maximum principal stress acting vertically. And then we also have got this one, which is the minimum principal stress which acts horizontally. So this one it acts horizontally, whereas this one is minimum stress, and this one is the maximum stress which acts perpendicular, okay, or vertically. Now, we also need to understand what you call the initial crack. We also need to understand what you call the initial crack, okay, direction. So the crack start at an angle. So the crack will start at an angle to this one. So the crack will start at an angle to alpha 1, and its orientation will always be influenced by the stress field. Its orientation will always be influenced by the stress field, okay. But now, we also need to understand the crack path. Okay, we also need to understand what you call the crack path. So, as stress starts to increase, okay, the crack will propagate along a path at an angle beta. At an angle beta. Okay. Now, what relative to the principal stress direction? So the crack will basically start to now follow the trajectory. Okay, that makes an angle to beta now. Okay, will follow this angle to beta. Okay, so basically that's that. Um, the most important part is the Griffith's theory. It focuses on pre-existing cracks. So it means that now the rocks already, they've got the micro cracks or the cracks within them, okay, that are already existing. Now, due to the tensile stress, the rocks get to be stretched. Okay. Now the stress will like to concentrate at the tip of these cracks. So that is to say, if the initial crack is there, now the Griffiths theory will focus on that crack, but at the tip. Now, so if the stress at the crack tip is stronger enough to break the atomic bonds holding the material together, the crack will start growing, leading to fracturing. Okay. So initially, the Griffith energy used surface energy to explain the fracture, but measuring this was very difficult. So later, researchers they modified the theory by focusing on how the stress concentrate at the crack tip instead. Now, can now see that if we were to apply the tensile stress on this one, we are pulling this material. If there is a crack at if we initiate a crack at the tip, okay, here at the tip, now the as the stress increases, the crack will always propagate along this path and will follow this crack because already we have initiated the crack. Okay, so I hope you follow. But I'll give you more examples to help you visualize this theory. Okay. Okay. Now, if you were to consider the paper, okay, the normal paper, if you were to try to stretch it this way and that way, it will become difficult to tear. It will become difficult to tear because of there is no cracks in this. All right. But now, if you make a small cut, if you make a small cut like this one here, you make a small cut, okay, the tear would now start to follow this micro crack. So now if you keep tearing, because you have introduced the micro cracks, now the tearing will easily follow this crack. Okay, so this happens because the stress concentrate at the tip of the cut, reducing the energy needed to extend the crack. So this has the same analogy with basically what's happening with the Griffiths theory. Now, okay, you see that if you keep if you keep on increasing the stress, now the crack will easily follow. Okay, will or the tearing will easily follow from this point all the way until we form a bigger fracture. So this has the similar analogy with the Griffith theory of fracture in brittle materials. So the paper fibers act like atomic bonds in a rock. So once a crack starts, the energy needed to continue breaking the bonds is lower. The energy needed to break this is lower than the energy released. Now this will allow the crack to propagate easily. So you can now see that here, that's where that's the tip that we focus on. Now if we have the small crack here, because we have introduced a crack here, the energy needed to continue breaking the bond is now lower than the energy released. Now this will allow the crack to propagate easily. So basically, that's what Griffith theory is all about. Okay. Now, the most interesting one as well is the Mohs theory. So it's often used in predicting the failure of brittle materials. We want to know at what point will this material fail. Okay. So the theory suggests that failure occurs when the Mohs circle at a point in the body exceeds the envelope created by two Mohs circle for uniaxial tensile stress and uniaxial compression stress. Okay, so we're basically going to be focusing on the what you call the this is what you call the Mohs circle. This is the Mohs circle. Okay. So this is the Mohr cycle, and this is another Mohr cycle. Okay, so Mohr cycle, it tell us much about the behavior of the material. So think of the Mohr cycle like the inflated balloon inside the container. Now that container is what we call the failure. Envelope. Okay, the failure envelope. So let's have this container. Okay, I want you to visualize this thing. This is a failure envelope. This is the container, failure envelope. Now you put the balloon inside this failure envelope. Okay, so this balloon is what you call the Mohr cycle. Okay, but now I want you to imagine um the failure envelope having needle kind of vibes. Okay, on the surface, I want you to imagine the nettles over here. Okay, I want you to imagine the nettles over here. Now, um the for this material, for the material not to fail, it means that the balloon yes, basically the balloon inside this failure envelope, it must be with of the reasonable size. It must be moderate. So I want you to imagine you inflating the balloon moderately. So if you inflate this balloon moderately, it means the balloon, it will remain within the container. So it means it won't touch these nettles. So there is no failure. So as long as this Mohr circle or this balloon does not touch this a failure envelope, then there is no failure. No failure. So it means the material is good. But now, if you were to overinflate it, uh, it will definitely touch the failure envelope. So if it touches immediately when there is a touch, okay, the balloon will definitely burst. So that's where we start to have the failure. So basically that is that. Looking at this diagram, this line over here, that's what you call the failure envelope. This line, it's failure envelope. So it means this Mohr circle, for as long as it does not touch this failure envelope, then the material does not fail. Then we are good to go. But if Mohr circle now start to touch this failure envelope, then the failure happens. So basically, that's one thing I want you to understand. That's Mohr's theory. All right. Yeah. So Um, what is Mohr cycle? Yes, I've been saying Mohr cycle, but basically, what's that? All right, Mohr cycle is a graphical tool used to visualize stress states in a material. So it helps determine whether a rock will fracture or remain intact under given stress conditions. So as long as this cycle does not touch the failure envelope, then it means the material will remain intact, will not fail. So the cycle represents the relationship between the normal stress, and the shear stress. So if you can check over here, we have forgot the normal. This is the normal stress and the shear stress, the normal stress and the shear stress. But I'll show you with this one. For example, this is the normal stress on your y-axis, and there is shear stress on the x-axis, sorry, and there is shear stress on the y-axis. So now um okay, that's why we're saying this cycle represents the relationship between the normal stress on your x-axis and the shear stress on your y-axis, acting on different places within the material. So, but what is the failure envelope? The failure envelope is that line which I showed you, that should there be a touch, should the Mohr cycle touch that, then the failure starts to happen. It means the material will fracture because it's no longer intact. Okay, so basically that is that. So the failure envelope is a boundary that represents the strength limit of that material. Okay, for as long as the Mohr cycle does not exceed that limit, then now the material is intact. So it shows the maximum combination of the normal and shear stresses that the material can withstand before it fails. So it usually determined from experimental data, that is to say triaxial compressional test. Okay, so what happens when Mohr cycle grows? As external forces or loads increases, the Mohr cycle expands. The Mohr cycle of that material starts to expand because the stress inside that material increases. Okay? So it means when you apply more stress on that material, now the Mohr cycle expands. So if the cycle remains inside the failure envelope, then the material is still safe. It won't fail. Okay? Because you are not touching the failure envelope. Because remember, the failure envelope is the limit. Now, but if the circle touches or crosses the failure envelope, then the material fractures because it's no longer intact. Because the stress conditions have exceeded the rock's strength. It means that that rock cannot withstand those new conditions. Then it will fail or it will fracture. Which is why these theories are worth understanding to the engineers and the geologists and other people, okay, who are building bridges, tunnels, malls, mines, developing new mine, and other things. Okay. Um, the like I said that if the Mohr cycle defined by the magnitude of the maximum and minimum principal stress component touches the failure envelope, then the rock will fail. Which is why over here, um, which is why over here so because of this Mohr circle, you're increasing the stress, remember, then the Mohr circle start to expand. So if it expands and touches this failure envelope, then now the material fails. But as long as this Mohr circle does not reach this limit, then the material is still good to withstand those high stresses. Okay. So this diagram is after Egbert, Julie et al. 2021. So and then this black one is what we call the criterion. Is what you call the criterion. Okay. This criterion is defined by this equation. Okay, is defined by this equation. This equation is this criterion. So failure criterion for a critically stressed fault. Mohr column diagram with the normal stress on your x-axis and shear stress on your y-axis, and a failure criterion, which is this black line. All right, defined by this equation. Okay, with the friction coefficient and the cohesion. Okay, so basically that is that about the Mohr. All right, so this one is very interesting as well. I hope you follow. um Now I gave you these three examples, so we know that um if you keep inflating the balloon, it will reach a point wherein it will start to burst. Okay, so because the failure happens because the internal pressure or the stress becomes greater than the material strength. Now it will no longer withstand those high stresses, then it will burst. So the bursting point is where the Mohs circle would exceed the failure envelope. I hope you understand. But also, if I were to give you the brick this brick layering, okay, we know if it's like this, it can withstand the high stresses for over millions and millions of years. Okay, for over millions and millions of years. All right, especially if these bricks are under compression, if they are under compression or squeeze from top and bottom, it will withstand these high pressures. But immediately, when you start to apply tensile and or shearing stresses, tensile or shearing stresses, like here, now these bricks would start to now fail. They will start to now fail. Okay, so it means now the the Mohs theory will predict at what combination of normal and shear stresses the brick will crack. Okay, and also this the biscuits. So if you were to squeeze it too much, there will be a point wherein this biscuit will crack. Okay. Now, last but not least, the stasis extension strain criterion, fracture of a brittle rock. So this states that the fracture will initiate when the total extension strain in the rock exceeds the critical value. Exceeds a critical value. As long as you exceed that limit, then the rock will or the material will fail. Okay, so this was reported to successfully predict both the orientation and extent of fracture. Okay, so initially, the previous researchers, they okay developed this formula. Okay, wherein the if you exceed this critical value, if you exceed this critical value or the limit, then the failure starts to happen. But now the new authors or researchers like Sengani 2020, it modified this equation into this one. Okay. So what is a strain? When a rock is stretched under tensile stresses, it experiences extension strain, or what you call the elongation. Okay, so the key idea of stasis criterion is fractures that when the total extension strain in the rock exceeds a certain limit. So let's say a limit is 10. As long as we are below 10, then we are still fine. But if the extension strain exceeds that 10, which is the limit, then the failure happens. Then the fracturing will happen. This critical strain value is different for each type of a rock. Okay, granite won't be the same as the sandstone. It won't be the same as the mud, rock, or shale, or whatever. So the criterion can predict both the direction and the extent of fracture, the direction and the extent of fracture. That the fracture would start from here to there, and at what in which direction. Okay. So I'll give you the I gave you the three examples. I gave you three examples of the stasis extension. The first one is the rubber band stretching. So the rubber band stretching, if you stretch it a little bit, it won't snap. But if you stretch it too much, it exceeds its limit. It exceeds the elastic limit, the limit wherein beyond that, then it will start to snap. Okay, so when the rubber band is stretched within its elastic limit, it deforms but returns to its original shape when released. So if stretched beyond its critical extension strain, okay, that this critical, this formula, the EC, the critical strain, immediately when the extension, remember this formula says, immediately when the extension or the extension strain is greater or equal to the critical one, then the failure will basically happen. Okay, so which is why we are saying that this rubber band, if stretched beyond it's a critical extension strain, the material can no longer hold it together and it breaks or fractures. So similarly in rocks, when extension strain exceeds the rock's characteristic limit, then the fractures will definitely form. And the other example is the mud cracks. Okay, is the mud cracks. So we know that soil in arid regions, when we have got high temperatures, now that these mud particle of the mud will basically lose its moisture content, and then when it loses this moisture content, with time it will start to shrink. Okay, because there is a less water content which it's holding the particle together. Okay. Now, this shrinking or shrinkage, it will create what you call the tensile stress. It will create what you call the tensile stress, or the pulling forces in the soil. Okay. Now, the soil cannot stretch infinitely, so it fractures where the tensile strain is the highest. So these cracks appear in network of polygons or in straight lines, depending on the type and the drying pattern. Remember, we said that these criterion, these stasis, will predict the direction and the direction and the extent of a fracture. So in rocks, when extension strain exceeds the critical value, fracture appear. Just like in dry soil, these fractures follow the direction of maximum tensile stress. So stasis criterion helps predict where and how fracture will form in brittle rock under stress. So the direction and the extent of fracture and where as well. Okay, then last but not least, we also have got the ice which expands and contracts. Okay, we know that during the day the temperature rises, now causing the ice to expand, but late at night when things are cool, then there's going to be a shrinkage. This expansion and contraction would put now the ice would put strain on that particular ice. Now cracks will now form. So when the strain becomes too much, okay, it would exceed that critical extension and criterion. Now the crack will start to okay. The cracks don't appear randomly, they form along the weakest directions where the extension strain is highest. So, just like ice, rocks in the earth crust experience stress and strain. When the extension strain in a rock exceeds its critical limit, then the fracture will always happen. Um, um, so in conclusion, the understanding rock fracturing, understanding of these three theories, especially when you combine them together, will give you insights into how and why rocks break under different conditions. Where in the Mohr's theory would put more emphasis on the stress conditions, predicting the failure based on the shear and normal stress interactions, and then the Stacey's approach built on this by incorporating the role of tensile failure in a rock mechanics, highlighting that many engineering failures occur under the tension rather than the shear alone. Now, in the end, the Griffith theory introduces the critical role of the microcracks and the flows which are already there within the material, demonstrating that the fracture strength is significantly lower than the theoretical predictions due to pre-existing defects. And now, when you combine all these things together, they form a holistic view of rock failure from stress-driven fracturing to the influence of inherent weaknesses. So by integrating these perspectives, geologists and engineers can better predict and manage rock behaviors in the mining, tunneling, and other mechanical applications. So understanding this principle is not just an academic exercise, good people, but also a crucial tool in designing safer and more efficient excavation and support systems in geotechnical engineering. I hope you guys enjoyed this lesson. If you enjoyed this lesson, don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. But still, if you are finding it difficult to understand this concept, you are more than welcome to comment on the comment section, and when I have time, I will be gladly help explain even further. Okay, and I'm sure you must be knowing what I'm gonna say next. I will always like to say, until next time, cheers.